Well, hello, welcome as we talk about the chemistry of the Earth. Brief review of Earth science here. So, here are the learning objectives. And let's talk about the Earth. The Earth has three main regions: the core, the inner core is solid, the outer core is liquid, and then we have the mantle. Mantle is kind of like a slurry, like cake batter, and then we have the crust. That's where we are. At least I hope you're on the crust of the Earth. I guess you could be in deep in the middle of the Earth without my knowledge, or you could be orbiting out in space. That'd be kind of cool. But anyways, lithosphere. This is the landmass, and the hydrosphere is the water, and then the atmosphere. Atmosphere we'll talk about next chapter. Okay, so here's a picture of the Earth, and if you wondered how we figured out the different layers of the Earth, we did it by earthquakes and looking at the different types of vibrations and looking at an earthquake and looking at the different uh, sensors of different areas of the world. We were able to figure out the shape of the Earth, the inside of the Earth. At least this is what we've determined based off of the earthquakes. So this is what the Earth's surface like the crust of the Earth, and it's mostly oxygen, and it's mostly silicon dioxide. So silicates make up much of the Earth, as does water. So you can see hydrogen, or it's basically silicates and water is what makes up the Earth's surface. And what are not included in silicates, here are some of the non. What a silicate is, it's a silicon oxygen. Sometimes has other elements in it too. Quartz being the most pure of that silicon dioxide. So iron ores are very important, as is aluminum. Aluminum is the most abundant metal if you don't count silicon as a metal. And galena, it's pretty stuff. It's shiny, and copper ore and limestone. And so we have the organic part of lithosphere. It's makes a small amount and of it, but we have it has the carbon containing, especially in the soil, and the organic molecules. And the nitrogen. Nitrogen is also important for growing crops and other things too, like phosphorus and potassium is important for growing crops and growing things. But we as humans, we've looked to use exploit the materials of the earth to improve our lives, and started off with sticks and bricks to form dwellings, and now we have the complex electronic devices much like I'm using to deliver this talk to you. And let's talk about silicates. So here are various silicates. So here's zirconium. If you were to cubic zirconia, this is that. We also have some long chain of spudimane. This is a source of lithium. Asbestos for chained. Well, it's kind of fibrous sort of structure, and this is now banned as fireproofing, but it's a wonderful fireproofing thing. Mica sheets. So this is it's similar to asbestos, but it's kind of sheet. Where asbestos is fibers, these are sheets of things, and it has vermiculite. It's very shiny and pretty. And then quartz has it's a different structure. It's a very um what is it? Tetrahedral structure. And we use this for many things, making glass, for instance. And there's various gemstones. So amethyst, agate, and citrine. They're very pretty. Okay, quartz, silicon dioxide. So if you take a geology class, they will say this is SiO4. And if you look at the picture on the right there, you can see why they call it SiO4. But the ratio of the atoms is SiO2. So if you see someone saying quartz is SiO4, they just mean it's this silicon in the tetrahedral oxygen tetrahedral repeated over and over again. So, but the ratio there is 2 to 1. So geologists and chemists like to argue about things sometimes. So you're in a chemistry class. So it's SiO2. Okay, so quartz is straight silicon dioxide, and it's a very common stone that you find. And micas, it's like SiO4, but in a sheet-like array. And mica is really pretty. It's nice and shiny. Asbestos is fibrous silicates and the straight line. It's a magnesium silicate, the crystalline. So this is a magnesium silicate, and now its use is banned because of asbestosis, damage to the lungs. Ceramics, we've been using lots of ceramics to make clay pots and whatnot, and that's in the ancient times. We use lots of ceramic. We've been using ceramics for various things. I mean, anywhere from brake pads to novel things. What's interesting about ceramics is that, I mean, you versus metals, we use a lot of metals. Metals, of course, can bend. Ceramics tend not to bend until they reach a certain point, and then they just break. So they're not as ductile and bendy as metals are, and alloys. Glass, we have a amorphous solid, non-crystalline solid, and ancient Egypt are the ones that discovered this. Took washing soda, sodium carbonate, and limestone and sand, heated it up, and it formed glass. Uh, we still use glass that way, but we have new types of glass. The soda lime glass, that's the stuff that that's the ancient Egyptians started using. Borosilicate glass, also known as Pyrex, that's what we use in the laboratory. So it's much more heat resistant. Leaded glass, this is also known as crystal, and it's really pretty. It can be used also to stop radiation. A lot of times, crystal glass is used around X-ray places, or if you like a window, if you want to look into for an X-rays. Colored glass. This is for stained glass. Different colors give um, different colors. Different elements give different colors to glass, and there's more. Unfortunately, with the burning of Notre Dame, we lost the rose window there. Gold was used in that for various colors as well. Photochromic glass. We talked about this before. This is the transition lenses where typically silver iodide is used. So okay, we use concrete and cement. This was actually invented by the ancient Romans. We talked a little bit about that, but this is how we do it in contemporary times. We take calcium carbonates and clay and heat it up. Basically, it forms the lime, the calcium oxide, and this is called clinker. And you grind it up, and then you add gypsum to it, and then you add aggregate. So sand, or you can use bigger aggregate, like you can see little pebbles like that in cement and in concrete in the ground. And when this hardens, it's known as concrete. How it hardens, you wet it and forms calcium hydroxide, and then that reacts with carbon dioxide in the air. It's also an exothermic reaction. It gets hot, and then that forms basically, well, it forms the calcium carbonate again with the stuff in it. You can also add steel reinforced. You put rebar into it to get steel reinforced concrete as well to give it a little more tensile strength. Uh, the concrete does really well on compression, not so well on tension for uh, for its strength. And steel reinforced concrete is especially important for earthquake prone regions. So Portland cement, so we've already talked about this before. It's how you make the cement. Here's a picture of it. Okay, so metals and ores. So what we tend to use, the simplest is Stone Age, where we just look for stones to form our tools. And Bronze Age, this is when, well, copper was first developed. You can find native copper, but copper is believed to be the first metal cracked from its ore. You can do this with a campfire. You can also do that with lead. If you put galena into a campfire, it's good enough to make lead. And you can with on the order of 10% tin, you can turn copper into bronze. There's different types of bronze, and all of it's 10% tin. And the bronze we use today has got various materials in it, but that's the original bronze. And then we have the Iron Age, when we started cracking iron from iron ore. We were able to make even better tools and weapons and so on. So I don't know what age would be, and I've heard it's called the nuclear age. I've heard it called the age of silicon. I'm not sure. It's debatable what age we are in right now. Okay, so here's copper, and it was believed to be the first one to crack in its ore. These are some pretty swords. And then bronze, it's originally was 10% tin, and it was a little better than copper. Bronze is fun to play with too. Iron, you need a little more. You need a little more heat. So if you uses the same idea with using carbon to reduce it. We talked about that carbon reducing uh, the um, the iron, and it forms carbon monoxide or carbon dioxide, and then it continues. Oh wait, so the coke forms carbon monoxide, and that reacts with the iron to form carbon dioxide. But carbon monoxide can also come off of it, so it's got to be careful if you work in a steel mill. And forms molten iron. And this iron was also referred to as pig iron, and this is a farmer's term. So, in the Industrial Revolution, the United States made a lot of iron. We still make quite a bit, but the uh, the raw material iron, it came down and formed bars, and it the farmer's like, well, that kind of looks like a bunch of pigs suckling on its mother, and that term then referred to these bars of iron being formed as pig iron. So it's a farmer's metaphor if you wonder where pig iron comes from. And basic oxygen furnace, it's a blast furnace. Oxygen is blasted into the furnace. So lime is added as well. And what the lime does is it helps draw out the impurities, and the impurities float at the top of the molten iron. That those impurities are known as slag. It's mostly calcium magnesium silicates. So okay, and the molten iron talked about that. The pig iron, and so then the pig iron is cast iron. You can put it with carbon, so you can have 2% carbon to form steel. That's known as carbon steel. Structural steel is 2% carbon. You can have other metals to add to it. So this is wrong. Cast iron is usually very low iron. It's, carbon steel is about 2%. You can go up to 10% to form iron carbide. That's what horseshoes are made of, and it's a lot stronger. But it's also very brittle. Stainless steel. There's a bunch of different types of stainless steels. They have different applications, and they're most notably for their corrosion resistance. Stainless, it does not stain. The steel doesn't rust. And uh, then we have just the various alloys do various things. This is an incomplete list. You have nitrided steel. That's to make tools, for instance. And like there's many different types of stainless steels, uh, and so on. So very abbreviated list of the alloys of iron. Aluminum is extremely abundant, and bauxite, and also we use cryolite to do it. Electricity is used quite a bit in the process. But the thing with making aluminum is it's makes some really kind of gnarly waste. I mean, because it's a very chemical process that has a lot of it's a very alkaline waste as well. So it can be dangerous. There was a spill several years ago in Hungary where there was some really alkaline water that came from aluminum production into the hydrosphere there. It can cause some damage. Uh, but aluminum used to be a precious metal. So in the founding of the United States of America, with well, I guess it wasn't the founding, but we had the Washington Monument, and we wanted to show how cool we were as a new country, and we have the capital of the Washington Monument be the very precious aluminum. And it's kind of funny now because aluminum is so much cheaper than it was back then. It was more expensive than gold. Napoleon used to have his guests dine off of aluminum plates, and his lesser uh, folks, he had them dine on the gold plates. So aluminum was the more precious metal, more precious than gold in the olden days. Now, of course, it's no problem. We have tons of it. Okay, so other sources. So indium is very expensive, and so use it. Uh, well, it's not listed here. What do we use it for? We also use it for diodes, so like LEDs, and we're saying photovoltaic cells. Lithium, we use a lot of lithium, mostly for batteries. Palladium for catalytic converters, yeah, that we use that, and platinum also for catalytic things. Rare earths, and you look at rare earths, it's like they're so rare, but you see we make so many of them, make 4 times as much as we do lithium. China right now is the primary source for it. There's other places that we can have it. United States has a source. There's quite a bit in Afghanistan, and also the bottom of the ocean is believed to have a bunch of rare earths. But we haven't quite tapped into those resources yet. But we really need the rare earths for many of the electronics. So the displays that we have. Uh, Magnets used very heavily. We need the rare earths. Europium, that is a rare. Oh, they're listed there to what they do. Yttrium, that's used. Well, you don't really use fluorescent light bulbs very much. Ceramics lasers, I used yttrium in one of my lasers that I use in grad school. Tantalum, and that's a very used for various electronics things. And tantalum's a very tough metal. It can be used. It's similar to titanium and alloy with titanium to make things like jet engines and whatnot for like fighter jets. Okay, and we are dwindling our resources. So, uh, and it's kind of sad. I mean, like you see a lot of these pretty ores. We've pretty much grabbed most of the easy to grab ores, and but it's harder to get our the high grade ores, but we're not diminishing that. So we're being mined, and it's harder to get to those metals, but we are still pushing on. And oceans may be the future, one of the future sources of metals. The bottom of the ocean specifically, maybe gold. There's gold dissolved in the seawater. And we're also getting more crowded. If the population is booming, so went from 1 billion in 1804, and now we're somewhere between 7 and 8 billion, and we're continuing to grow. So we'll see what's going to happen. We might reach what's called a Malthusian catastrophe, where we can't support our population with our resources. And there we are at the end of this. So come and join us next time as we talk about the atmosphere.